We are at 8:10, so I think it's about the time to start. There are two chairs, Robert Eriksson here and myself, Mladen Kezunovic, and we decided to share the task, so I will be introducing the speakers and monitoring the presentations, and then Robert is going to take over for the panel. We're not going to wait much longer, so the first paper is by Amina. Is that correct? Okay. And what I suggest is you come forward and you introduce yourself and your paper, please.
Thank you. So I have to stay over here so you hear me. Okay. Hello, everyone. Good morning. I hope you're all doing well since the night we have yesterday. I would like to thank the organization and the members here for the night we had. So as you can see, my name is Amina Benzerga. I'm from Belgium, from University of Liège, and my advisor is Damien Ernst. Maybe you know him. So I'm here today to present you the paper we worked together on, and it's about the optimal connection phase selection of residential distributed energy resources, so DER, and its impact on aggregated demand. So mostly how to connect PVs and other DER. So I think you all know by now that DER are increasing, and they are, at least in Europe, increasing a lot. So DSO do not control their location and their size, which is a big issue. So what do we have as an issue? We have people buying new PVs or any DER. They're placing them everywhere they want. This is producing, so we have variability and uncertainty in production, and this causes some phase imbalance. So what do we do when we have phase imbalance? We curtail, and people are not happy when we curtail, at least in Belgium. I don't know how you feel in here. So what was our aim? Our aim was to find a way to optimize the hosting capacity, and we do that by finding the best connection phase for new DER. This is done with the aim to invest less money in the network. So what do we need for our methodology? We need a low voltage network, so this is a lot of data we need. We need the topology, we need the impedances, and we need a DER type to assess. For later, we'll talk about PVs. So the test case will be on PVs, but you can use anything. We need all the DER that were previously installed. So this is also a data that we need, and the new one you want to install. So the method, as you can see on the left, right, has two phases. The first one, is individual selection. So what we do. First, you want to buy new DER. You ask the DSO and you say, I'm going to buy one, where should I connect it? And the individual selection is about stating, like, finding the best phase just for you for the new DER. Then, once we compute that, we end up with a cost and a phase. That is the only thing to remember, so the IS cost and the IS phase. The second step is we do global optimization. So for this one, we take all the DER that are in the network, and we do an optimization to find the best set of connection phases. To do that, we use genetic algorithm, and this output for each phase, that, like each DER that we put a phase. It could be the same one as before or a new one. So once you have that, you have the GO cost, the GO phase, and actually this cost, if you want to change someone's phase, it costs money, so we added the GO cost of correction. So then you have those costs to compare. If the IS cost is smaller than the sum of the others, you just change the phase of the new one, so you connect it to the phase you find first. If the cost for changing several DER are smaller than the cost of just the first one, you do change the others. Pretty simple, right? So what is something that we can change in our model is the cost function first. So we defined it as the curtailment cost and the network loss, but you could add any cost you want. So for us, the network loss is what you put in the network and what goes into loads, like minus. The curtailment strategy, we only use a simple one just to check if the method worked. So this simple one is just checking if we have overvoltage. If we do have overvoltage, we curtail all DER, not just the one causing issues. And we compute a cost for the money that the people weren't able to make out of the energy that they produced, sorry. So the test case, this is a beautiful network in Belgium we have. You can see the different colors are the different phases. The gray one is the neutral one, so it's a 3-phase unbalanced one. We have 128 customers. We use 1 month time series for the cost computation, and we assume so PV production and the consumption of the people, so the load. We took that from a London data project, and the PV are from Belgium. So the results on PV. As you can see on the table up there are the costs in euros. So the first one, you can see that the IS cost is really high for all 3 phases, and you see that the geo cost is really small. So even adding the correction cost doesn't go as far as the first cost, like not doing anything. And you can see on this figure that if we don't do anything, so as it is done now, so what we do now is you connect your PV to the connection phase of the house, you would have a much higher cost. So this is the kind of blue line, and the green one is one with our solution. And you can see, so the first one, we computed the curtailment, and you can see that there's a lot of curtailment, but with our solution, we were able to remove all curtailment for that example. So you see that the big part of the cost function is the curtailment. So removing it is really good for operational cost. So next, we wanted to see how uncertainty plays with our tool. So for the first one here, we did use real data. We used the real-time series for the PV and the load, and here we decided to add errors in the time series. And you can still see that the costs are much lower than the one without our solution. So we can see that both figures are smaller and they follow the same path. So this is not optimal, but it's still better than what we are doing with less investment. Finally, we had the results about the aggregated active power demand. This was computed with what we had as load and what we removed with the PV production. And you can see here the impact. So avoiding a frequent PV curtailment, we were able to have a more balanced phases. Then we have like improve the demand during the day. And finally, what you could see, that is a note to say that the absolute value would be greater with our solution, but still we were enhancing the production of PVs and not checking only the loss function, because the curtailment cost was bigger, so that was what we wanted to minimize. So as you can see, a simple thing that the DSO could do could have a real impact on higher voltage. So a small conclusion. I hope I'm on time, but I should be really on time, I think. I'm speaking fast. So what we want to do is have a bigger hosting capacity. What we want to do it without investing most of money. So what we do is have a practical tool that DSO can use. And and what we had was result on a Belgium network, and we were able to accomplish low curtailment and low network losses with a simple solution. So the computation time, we used 5 new DER. So normally you would use the tool with only 1 at a time. So we had 12 hours, but I think you can really optimize that. The limitation, as I said, is the data requirement. But we did a first paper on the data, the network topology. So we assume you can reuse that, and also that you only can compute it for one type at a time. So you're either doing PVs, you're within wind farm, or another type, but everything is at a time for the moment. The advantages is you have a practical tool that you can really use now, and it's applicable for any distribution system. You can we give like real results that you can easily understand and work with it, and we need no network investment. So you do with the data you have kind of now. And I think that's it for me. Thank you.
Thank you very much.
Oh yeah, I forgot about the question. You go ahead.
Okay, so we have time for one question. So Any questions out there? Okay.
Gregor Verbich, University of Sydney. So just one question. This raises a question of fairness. It might happen that your neighbor gets permission to connect, I don't know, 5 kilowatts, and you get your permission denied. Did you, like, maybe just, what are your comments on that?
Can you repeat the beginning of the question, please?
So this raises the question of fairness, right?
Fairness.
Because your electrical location on the network determines whether you will be allowed to connect your PV system or not, and the size of it.
Yeah, I think in Belgium you don't have the choice, so you have to accept everyone. So if you have an issue in Belgium, that's the case, that's how I was explaining it. So if anyone wants to connect, like if everyone in your street wants to connect PV, you can. So if there is an issue, you can complain and they would have to reinforce the network. That's why we want to use this before, because that way you would be able to connect it the best way without investing first.
Yeah, and that's exactly what I'm saying. The best way means that it's can be unfair, or can be...
Why?
Isn't it the case that the amount of PV you're allowed to connect to the system depends on your electrical location on the network?
Yes, but at some point you would have to invest. Like this is in the case where not everyone in the street buy it, but at some point you would have to invest. Like even, I think that this delays the time you would have to invest in the network, but if everyone in your street is buying it, at the end you would have to reinforce the network, right?
Okay, so you are still allowing everyone to connect the same amount of PV. It's just that the question, where do you reinforce the network?
Yes, so I'm not sure I understand quite your question, but
Okay.
I would go around.
Yeah, maybe.
Yeah, maybe you can
Okay.
continue, you know, at the break or even during the panel too.
Okay,
Okay.
It's a very good question, by the way, so it's worth exploring in the panel perhaps.
yes, okay.
Okay, so
Yeah, thank you.
we have one more, Mr. Canizares.
Claudio Canizares, University of Waterloo. Interesting work. Haven't thought about this. However, my question would be, at least in North America, choosing the phase where you connect your PV would not be a choice because it's a single phase transformer typically.
Oh,
So would that be the case here?
no.
So
That's why
every user has access to the three phases?
No, the thing is, as you see, like the network here, you would have access, and that's why we call the labor costs. So from the street, you would have the three phases, and then you would just have to connect the house to that phase. So that's
the
what.
low voltage, you have a transformer in between, so that's what I wonder. At least in North America, you don't have access to the three phases.
You do have access to
Okay.
three phases. That's why we just have €100 cost per connecting just the house.
So every house has access to the three phases? That's
No.
what I'm asking.
Normally, I was told to, yes.
Not in North America, so you only have one phase. So
Okay,
you
in
cannot choose the
Belgium-
phase you connected to.
Oh, I didn't know. So I think this would add in the operational cost, like the labor cost. This would mean like we have a much higher labor cost. But as you can see here, I think even having a bigger cost, like labor cost, will still lead to optimizing better, I think. It
All
would be
right.
interesting to see with North America data, I think.
Very good.
Thank you.
Thank you once again. The next paper is by Professor Kostas Urnas. So I will introduce Professor here, and if you can then talk about the title and yourself as much as you feel is appropriate.
Okay, thank you, Mladen. This is the work of my PhD student, Yorgos Prionistis, and I will be presenting this paper on active distribution network flexibility and use of this flexibility to increase voltage stability margin. Excuse me. There was much discussion in this symposium about flexibility. The difference in this approach is that we determine flexibility not for the market, but for control. So in this application, we discuss about how to use this flexibility to increase voltage stability margin. So I don't know if I can, okay, I can show from here, okay. So the idea is to provide, as I said, voltage stability support to the transmission system. And the approach used here is that we assume that in every active distribution network, we have one controller who is exporting to the control center the flexibility region in terms of P and Q in consumptions at the connection point. The transmission system operator, as usual, sees the transmission system up to the high voltage bus and has no information for the rest of the system, but the local controller is the one that knows the system and offers the flexibility. Then the transmission system operator can use this flexibility by sending reference P and Q points to the local controller. So this in this application, the goal is to increase voltage stability margin, but there may be also other applications of this approach. This is a rough idea of what we mean by flexibility region. This is the operating point, and according to the analysis made at the local level, the actual flexibility region is computed with a technique that I will show, actually two different approaches. And we'll use optimization both for determining voltage stability margin and for determining the flexibility region at the active distribution network. So this is a multi-step approach. First, the control center determines the voltage stability margin, assuming consumption at the high voltage substation level. This is done for all possible contingencies, and the critical one is the one with the less margin, but all of them are monitored. Each active distribution network is calculating, using optimization, the flexibility region periodically, for instance, every hour, and this is exported to the control center. Now, if the voltage stability margin for specific contingency is considered insufficient, then the control center can solve a new optimization problem, taking into account the flexibility. Now, one thing that should be made clear here is that during this approach, we do not shed load, so there is no effect on the customer, but we have an indirect load reduction due to maybe voltage and so on. But it's within what is considered acceptable to the customer. So the new optimization problem is done preventively to increase the voltage stability margin for specific contingency. And then the last phase is that the active distribution network controller has to take this set point and adjust local controls so as to achieve the required set point. Now, this is the optimization problem for the flexibility region. These are the network constraints in Cartesian coordinates. We respect voltage limits on all nodes within the distribution network, and we have the maximum current of all converters in the network, and we also have a condition for power injection by the distributed generators. This is, I mean, if you don't have any type of energy storage, your PGK will be constant. But if you have batteries, we can assume that for the time necessary to do this emergency type of control, there will be enough energy in your battery to change your set point. So if we assume the battery is connected on the same, for simplicity, on the same node where we have the converter. So behind the converter, we assume a source that may be controllable or not, depending on the application. We have two ways of solving this point. I mean, this problem has to be solved for a range so that we can get the whole flexibility region in the PQ space. There are two ways of doing this. The one approach that can be used in small, simple configurations is to identify points where you have multiple binding constraints and then connect these points by line segments. The second approach that we'll describe later is to do a radial scan for various power factors of the change, of the consumption that will give you a number of points that we then formulate into a polygon. But I'll show this in detail next. So the case with binding constraints, as I said, can I have a glass of water, please?
I'll do it. All right. Thanks a lot.
Sure. Okay. So if you have a two-bus network, then it's very simple to compute multiple binding constraints. Ian Hiskins has used this technique in larger systems. So what you do is you assume, for instance, that your bus here is at the minimum voltage, and this bus here is at the maximum. And this is so this will become a slack bus. The other will be a PV bus. And then you have a direct solution, and you check if all the constraints are met, it's acceptable. So it's one corner point. Another case would be this is in the minimum, and then the reactive power of your source is at the maximum, so you have a slack bus, a PQ bus, and then again you compute the point. So you see here, these are the multiple binding constraints that are feasible, the red dots, and this is the number of points computed with the radial method that we'll describe later, and you see they very much are close to forming irregular polygon. So this is the one approach that is more explanatory because it's only for very simple configurations. But then we go to this radial scan thing that can give you a solution to a general distribution network. So the idea is to set an angle between the delta P and delta Q, and you go along this line to find the maximum and minimum, and you get 2 points for every angle. So in this case, we have done this for 120 points by changing the angle by 3 degrees at a time. Now, let's go to this polygon approximation I was referring. We have a general area that is not necessarily convex. We don't have any assumption there. We start with 3 initial points so that we form a triangle. And then we take all the exterior points outside the triangle, find the one that is the largest distance, and then include this as a new vortex in our polygon. And we can continue until we find the number of vertices we would like. In this case, we stop at 6 vertices. I'll show it pictorially. It will be easier to see. So the initial triangle are the red dots. So I take this one, maximum P, minimum, maximum Q, minimum Q, this one here, and maximum P, the other one. And this is the first triangle. Then we find one by one the other points, which are the purple ones, and we form this irregular polygon, which is an approximation of the flexibility region. And then what we do, this is for a general network. By the way, it's 30 bus. We've taken from a paper by Petros Aristidou. And we have 5 converter interface generators. And in this case, we assume that we have also battery energy storage. Okay, so this is a representation. I say it's an approximation. We do not have any guarantee that all the points are feasible within. But what we know, since this will be an offer made for 1 hour, we know that within this hour things may have changed. We also, when we do this analysis, we assume that the voltage at the medium voltage level of the substation is fully controllable, which might not be the case because of things that have changed in the system. So this is, in the last stage, since we cannot guarantee that the point is feasible, we go as close as possible to this point. So without going into much detail, this is the central OPF problem to determine the voltage stability margin. The difference is that when, I will not go to much detail here, but where are the constraints? Just a moment. Okay. What I'm saying is that 7, well, yeah, okay. I forgot to point out that finally these 6 straight lines that form the polygon are given to the central problem as linear constraints. So in the central solution, if we don't consider flexibility, we get voltage stability security margin. If we consider flexibility, we get the maximum voltage stability margin. This is an application on the Nordic test system, shown also yesterday by Hane of Chalmers University. And here are the 6 flexibility regions. The point here is that comparing with earlier works, in this simple configuration, we always go to have the lower voltage at the MV bus and the highest voltage on the other bus. If we go to more, well, using this approach, we have initially an unstable contingency with a negative VSM, and you see by using 5 active distribution networks, eventually after the third one, the system has been made secure, and if we go all the way, we can have even a positive margin. I will not show the details here, just one last case study, time permitting. This is a very simple radial transmission system where we have the active distribution network with the 30 buses. In this case, we saw that initially the system has a small margin, margin 113 megawatt. By using, taking advantage of the flexibility, it can increase by 10 megawatts, but this is 30% of the nominal capacity of the converters in the system. So it's not that little after all. And then these are the set points given to the active distribution network. And in this case, it is able to go and exactly find this consumption. So the solution of the problem, in this case, the minimum, because the problem that is solved after this set point is given is to minimize the distance of the consumption from the set point. And in this case, it can go exactly to 0. So this is all I had to report, and sorry for being a little bit late.
Thank you very much. So we are ready for questions. Any questions out there? Patrick?
Patrick Manciatici from RT France. Thank you, Costas, for the very interesting presentation. Just could you elaborate a bit on the fact that we have these capacitor banks that are connected, and then we control the voltage also with the capacitor bank on the.
Yes.
And then could you extend this with this kind of controls that are already existing in the system, or that create a lot of complexity?
Yeah. Okay. This is perfectly valid point. In this case, we use the LTC to control the voltage of the substation. So we could also use switching capacitors, and this will be another source of flexibility if these capacitors are in the distribution network. In this case, we assumed the converter interface generation and the possibility of having batteries. But also capacitors are also something that will play in this control. If the capacitors are in the high voltage side, then it's part of the transmission problem to be addressed.
All right. In interest of time, we're going to move on. Thank you very much. Appreciate that. Next speaker is Professor Stephen Lowe, and he's going to set up his computer here shortly, and we're going to take off from there. So thank you, Stephen.
Thank you. So just need to connect this. And the audio? Okay. Well, thank you very much. My name is Stephen Lowe of Caltech, and I'll talk about three-phase power flow networks. Okay, so let me start by saying what this talk is not about. It's not a new model or new discovery. It's not a new algorithm or power flow solution. What I hope to do is to propose a simple and unified perspective to think about three-phase power flow. And hopefully you'll provide some structure and clarity in understanding some of the subtle issues of three-phase unbalanced power flow. And hopefully it can be helpful to educate our students or even simplify unbalanced power flow optimization. So if we think about how we build a model, we build a model for the device, and then a model for the line, for the transformers. We put them together through either nodal currents balance equation or nodal power flow equation. So I equals YV or a power flow equation. And then that's the overall model, and then we can develop optimization algorithms, OPF, and solvers, and so on to solve them. So this is the same for single phase or three phase. The difference between single phase and three phase really is that the three phase device models are a lot subtler and sometimes confusing. And therefore, that will be the focus of the talk. So I will spend about maybe, hopefully 12 minutes on how do we think about three phase device models, and then maybe 3 minutes of say, okay, how do we put all this together and then develop, say, analysis, optimizations, and so on. So the key question is that how do we derive external models of three-phase models? And they can be different devices, say voltage source, current source, constant power source, or impedance. And they can be in Y or delta configuration. They may have neutral lines. or not. They may or may not, the neutral lines may or may not be grounded, or the device may or may not be grounded. The grounding impedance may or may not be 0, and so on. So again, I would try to propose a simple and unified method. Nothing is new. We understand a lot of these different pieces, but how do we put them together in a very simple manner? And the idea is very simple. There's only two ideas. One is that the external model, which determines the external behavior that's seen on the network, right? So if you think about the network equations, say the I equals YV or the powerful equations, it really relates the terminal variables that describes the external behavior of the three-phase devices. But the three-phase devices have their internal behavior, whether it is a voltage source or impedance and so on. And the first thing is that we can just write down this one phase, the internal model based on the behavior of the single-phase device, independent of whether it's in Y or delta. And then we need a conversion rule to convert between the internal behavior and the external behavior, and that's all it is. So once we write down these two set of equations, you can eliminate the internal variables, and then you get a relationship connecting or relating only the external variables, and that is the external model which you can use to write your network equations. So the rest is really filling out the details of this, and this is basically all it is. Okay, so starting with the details, the internal variables, which are the voltages, currents, and powers, are simply the voltage, current, powers across each single-phase device, independent of whether it's in Y or delta. And therefore, the V of Y, which is a three-dimensional vector, is simply V, AN, BN, CN. Right? This is basically the single-phase device, whether the device is voltage, current source, power source, or impedance. And IY similarly is the current across single-phase devices, and so on. And the power is very simple. Once you have the voltage and current, you take the component-wise product, VI complex conjugate, then you get the power. So let's just focus on the voltage and current. And then for Y configuration, you have some neutral voltage, neutral currents, and so on. And again, it's very general. The device can have neutral lines or not, be grounded or not, zero grounding impedance or not, and so on. Similarly, for delta configuration, we have internal variables, which are the voltages, currents, and power across each single-phase device. And therefore, V of delta is simply V, AB, BC, CA, and similarly current. And then we have these terminal variables, which are the 3 lines or 4 lines coming out of the device. And we have voltage, currents, and power. And the voltage will be the voltage between, say, the line and a common reference point, say, the ground. Right? And the current with the current on the lines and so on. So these are the terminal variables that describes the external behavior of that device. Okay, so the external model, which is simply relationship between these terminal variables, right? They depend on 2 things. They depend on the internal model, what that device is, and it depends on the conversion rule that converts between internal and external models. So and the key, again, is that these devices interact with the network through the power flow or current balance equations, only through the terminal variables. So they don't see the internal variables. And therefore, because it depends on 2 things. The internal model, which is simply a relationship between the internal devices. So the voltage for the Y configuration or voltage for the delta configuration, which, again, is simply the voltage across each single-phase device, independent of the configuration. Okay? So they are independent of the configuration. It depends only on the behavior of the device, which I consider 4 devices, 4 types of devices: voltage source, current source, power source, and impedance. You can have more. And then the conversion rule that converts between the internal variables, the stuff with superscript Y or delta, and the terminal variables without the superscript. And it depends on only the configuration, but not on which device it is. Right? It doesn't care what that box is, voltage source or impedance. So let's look at the conversion rule. Okay, so we look at the conversion rule, and then we look at, for each of those devices, what is the internal model, and then apply the conversion rule to extract the external model. So the conversion rule for Y configuration is very simple. V of Y is the voltage across internal devices, the 3-dimensional vector. Vn is the voltage of the neutral. 1 is the 1 vector, 1, 1, 1, right? So, and therefore, you have a very simple relationship between the terminal voltage V and internal voltage Vy, and similarly for the current. Okay? So given one, you can figure out the other. And the power, again, you can take the component-wise product, Vi plus conjugate, you get the power. So ignore the power. Okay, very general. The conversion between internal and external models for delta is less subtler, but it's still pretty simple. It looks like this. So this is a vector, which is simply this. Right? This is simply this, and there's a matrix I call conversion matrix. This is a familiar gamma matrix. You can think of that as an instance matrix of this graph. Gamma transpose is the instance matrix of this graph, but in a reverse direction. So you convert between the internal voltage and terminal voltage, and similarly the internal current and the terminal current. So we want to be able to go from the internal to the external, or it's external to internal. But gamma is not invertible, it's rank 2. But we understand a lot about the matrix, and the spectral properties of gamma is important. So gamma is not symmetric, but it's a normal matrix, and therefore it's unitarily diagonalizable, and its spectral decomposition looks like this. So these are the eigenvalues. These are the eigenvectors. So alpha is e to the minus 120 degree, doesn't matter, but alpha plus is this vector, which is the eigenvector of this gamma. And this is the positive sequence balance vector, 1 alpha alpha square, and 1 alpha square alpha is the negative sequence. So it turns out that the reason the balance per phase analysis and the balance interval works is because this positive sequence is the eigenvalue of this. So we probably won't have time to get into the details, but anyway. So with this, you can figure out, you can compute what is the pseudo-inverse of gamma and gamma transpose. It's very simple. You just essentially take the transpose. And therefore, this allows us to convert between internal and external. So for delta configuration, then these are the equations that convert between the two, the one that we saw before. Right? And therefore, given V, then we can figure out the V delta, and given V I delta, we can figure out I. But given V delta, we can also figure out V if the given V delta is orthogonal to the one vector, basically. Then in that case, the V is a pseudo-inverse, but then importantly, there's a aperture constant, which is the zero sequence terminal voltage. Now, typically in the problem, depending on the problem that the applications, we're given sufficient information. Let's say there's a reference voltage in the network, for example. Then that will allow us to figure out what gamma is. But we cannot just assume it's zero. It may not be your application. And therefore, you will get the wrong solution if we don't keep track of what gamma is. If we don't, again, in the absence of those additional information outside this model, then there is an aperture constant. Similarly, given I, there's an internal voltage vector, which is given by this, and beta is this aperture constant, which is the zero sequence internal current of A delta. So how am I doing on time?
We have about 4 minutes.
4 minutes, okay, so I will speed up even more. All right, so that's a conversion, okay. So again, this is really the key. That is, okay, so how do we build a model? Well, we write down the internal model based on what device it is. We apply the conversion rule, which are those a couple of equations. And then we can eliminate the internal models to arrive at a relationship between the terminal, right? Whether it is in Y or delta, grounded or not grounded, and all of that. And the rest is just fill out this detail. Let me give you one example to illustrate. So let's say we have a voltage source, right? It's not necessarily ideal, so there's these diagonal entries of the impedance. So this is the internal model that describes how voltage source behaves. This is the conversion rule that we saw before. Eliminate the internal variable. So interestingly, for the single phase, then the relationship between the external voltage and current is very simple. You can go from one to the other. But in a three-phase, is asymmetric. So given V, the relation you can map directly, uniquely into the I vector, terminal current. But given I, you can only determine the voltage up to a constant, zero sequence voltage. And the reason is because this contains more information than that. So let me leave it at that. So this is the relationship. It's very simple. A couple of manipulations, you get this expression. Right? And similarly, given given, okay, anyway, let me just compare. So this is a single phase, or this is a three phase. This is a lot a little bit more complicated expression. It didn't show on the previous slide, but it's really simple to derive. Similarly, z delta depends on the given impedances and also the configuration. That's the second equation. Is a little bit work. So it doesn't work. Oh, okay. If it is ideal, then you reduce this. It's simpler. Conceptually, it's very simple. So again, this is zero sequence voltage. Impedance, same thing. Let me just jump to, okay. So again, single phase and three phase, structurally, they really are the same. Here's a tiny bit of details. Once you figure out those details, actually everything is quite simple. So this is one example. Single phase, this is how the single phase impedance works. This is how the three-phase impedance works. There's this Z delta that depends on the configurations, and then and also that conversion matrix, and then this gamma, which is the terminal zero sequence terminal voltage. Okay. So if you assume, for example, very often that is assumed in the literature, that the impedance are balanced, then it reduces, it becomes simpler. Right? Everything just fall out from that simple equations. Okay, so these were the external models that involves only terminal variables that you can use. Okay, so let me just 2 minutes. So this is a line model, right? So it looks very similar, well, it's the same. Whether it's a single phase, whether it's a three phase, whether you use 3-wire models or 4-wire models. The only difference is that whether this is a scalar or 3-dimensional vector or 4-dimensional vector. So these are the series admittance matrix for three phase and shunt admittance matrix and so on. So that's the standing end current. That's the current balance, which is just this, right? And then you can express this into the voltage. That's the I equals YV equation, right? Or you can write power balance equation. So this is the complex power injection at node J. These are the voltages. This, if you look at the three-phase, single phase, it looks the same. Okay, so again, so what do we do? Well, you have the device model. You can either use external model, which involve only terminal variables, or the internal variables plus the conversion rule. That would be the equation you use in your optimization, for example, right? So if I need to optimize over internal variables, then I would do this, for example, right? But you can use either, just depends on your applications. And if you only have voltage, current, and impedance, then everything's linear. If you have a say constant power device, then inevitably you will have nonlinearity. On the network, though, you can always use linear current balance equation. So this is always linear. Whether your overall network is linear or nonlinear depends on whether you have a constant power source device. Okay, I'm done.
All right, very good.
What? One more minute? Can I have 1 more minute? Just make a comment. Okay.
30 more seconds.
All right. So the three-phase analysis is that you have a set of devices. There can be different devices in different configurations. You specify whatever it is, and you want to calculate all the remaining variables. Okay. So that's the analysis. To write down the equation, solve numerically. If you do optimization, it's the same process. It's uncontrollable devices, you specify them, those are in the blue, and then you have some costs over the controllable variables or states. So those will be the subset of these variables, and then you write down the equation, write down the adjacent additional constraints, you solve numerically. So I will stop here. For the balance, the interesting balance thing that I was
Thank you very much.
Well, one thing, though, is that the reason I'm very excited to have this opportunity to present here is because I love to get feedback from you to see how this can be useful or not. So if you're interested, there's a draft book. It's a draft. It's incomplete with inconsistencies. I'd love to hear from feedback from you or any corrections and pointers. Thank
All
you
right,
very much.
very good. So we are ready for questions. One question, that is. We have a lady, and so we will, Maria, why don't you go first? Sorry, you will have a chance too.
Talking about ladies. Okay, anyway.
You have only 15 minutes, Maria.
Sorry. So, Steve, the idea of breaking it into internal characterization, which is always very complex, and then terminal specification, I think it's a great one. I thought a couple of nights ago I gave my talk. It's exactly the same idea. The specifications on the terminal connection is always simpler. And then, so we are struggling a lot with converting from from internal to terminal is good. But this pseudo-inversion is a little bit bothersome, so I'm wondering if you can comment on that a little bit.
Yeah, so I guess you're referring to the delta, the conversion for delta where there's this arbitrary constant, right? So I think, for example, typically for a problem, again, it depends on the applications and the specific question we ask. Typically, for example, if we know, say, all the neutrals are grounded, for example, then that you fix, or there's a reference voltage, then it fixes that constant, for example. And therefore, it depends on the question we want to pose, what information we have and what information we want to determine. Typically, for analysis problems, you're given a set of specs, and then they would have just enough equations to determine whatever remaining variables. In that case, those arbitrary constants will be determined.
We can talk later.
Yeah.
Pseudo-inversion basically doesn't give you unique solutions.
That's right. Sometimes we may not have enough information, then indeed there will be some arbitrary constant. And this is where we need to be careful, because otherwise we get the wrong equations when we solve our OPF. Yeah.
Right. Okay, very good. And one more quick one, and then we are going to proceed.
Yeah, thank you. Nawaf Nazir, Pacific Northwest National Lab. I had a question about, so you're using the formulation, it's a current injection one. Just wanted to ask, like in your experience, if you use some other formulation, would the same analysis hold? Or is there like a particular one which has the symmetry between the single phase and the three phase?
You mean the power flow equation, different right. Power flow? So the different power flow equations can all work. So that's only determine the current balance or the power balance on the network. So once you figure out the terminal or external behavior of the devices, three-phase devices, you can just plug into the traditional framework. So yes, you can use different power flow equations, polar, rectangular, whatever.
All right. Thank you very much once again.
Thank you.
So we are moving on. We are pretty good on time. Thank you all, presenters so far and discussers. Professor Gregor Verbich.
Thank you.
Oh, he's already behind. Okay, sneaking. Why don't you please introduce your talk and yourself? Thank you.
Okay, morning everyone. Yeah, so my talk is on operating envelopes which are used to limit the amount of power prosumers can inject into the grid to prevent overvoltage and network congestion issues. So I'll start by discussing a little bit the motivation, and that's a snapshot of 1 week last spring in South Australia. So if you're not familiar with the geography of Australia, this is Queensland. And the national electricity market is the interconnection spanning the eastern seaboard, so Queensland, New South Wales, Victoria, South Australia, and Tasmania. So the name national is a bit misleading because it's not quite national and doesn't include the Western Australian Northern Territory. But what I'm trying to show is that in South Australia, which is here at the edge of that long stringy network and quite weakly connected only to Victoria, even though it also borders New South Wales, is that rooftop solar can occasionally supply all the load. So this here, well, you should be able to see this bright yellow is rooftop solar, dark yellow is utility scale solar. On that particular day, it didn't quite cover all the load, but there were certain instances where this indeed did happen. So again, this is just coming behind the meter. And this is creating problems, and moving into the future, this is the prediction from the CSIRO, which is our national lab. So currently we are at around, I think, 12 gigawatts worth of just rooftop solar, and peak demand is 35 gigawatts. And the prediction for, this is up to 2050, goes all the way to 50 gigawatts, according to the scenario. And the installation of battery storage is still like just about to experience a boom, so especially now with the prices have increased so much. So long story short, in the future, we expect that up to 40% of power will be generated behind the meter using rooftop solar coupled with batteries, and this will result in a highly decentralized power system or power system supply. This is taken from, well, this is actually AEMO and Energy Networks Association in their Open Energy Networks discussion paper in 2018 used that reference, which is originally produced by Bloomberg. AEMO's forecast is maybe a little bit less bullish, but at the moment in South Australia, over the whole year, almost 20% of energy comes from behind the meter already. Across the NEM, it's close to 10%. Queensland, a little bit more than 10%. But almost, so around 10% in the national electricity market, around 10% of energy is already coming from behind the meter resources. So now, so what we have to, so what we currently do to deal with those resources, they can be just seen as a problem, but there's actually a better way, and it is to aggregate those resources into virtual power plants. So if we look at the conventional deregulated power system structure, so we have the DSO, the retailer, and so on. So now we have those VPP aggregators, which can be the same company as retailers, but for the sake of the argument, I'll treat them as a separate entity. So essentially, they aggregate a bunch of prosumers to provide all kinds of services. They can play in the energy market, ancillary services market. They can provide network support. And the important thing is that they have to coordinate that with the DSO to prevent over voltages in particular, or even reverse power flows. So how do we formulate that problem? Well, we can formulate it as a canonical optimization problem where we minimize some cost function. That's typically cost minimization, can be profit maximization depending on the scenario. And the decision variables in that optimization problem include decision variables from the aggregator, user agents or the prosumers, as well as the network decision variables. Now, moving to the future a little bit, we actually trialed that in a Bruny Island battery trial which concluded a couple of years ago. So we implemented a distributed OPF to coordinate a bunch of behind-the-meter PV battery systems to solve a network congestion problem. So this is on a small island just off the mainland, Tasmania, connected to Tasmania with by an underwater cable that gets congested during peak time periods. So traditionally, they used diesel, a couple of diesel gensets, and Task Networks, the network service provider in Tasmania, they figure out that maybe it's better to source that additional capacity from rooftop solar and batteries. So we implemented a distributed OPF solution to coordinate all those devices in a distributed manner, and we also developed reward structures, nonlinear pricing to reward customers for participating in that scheme. And also we did a social science experiment to see how customers react to that. Anyway, I don't have the time to go into details. If you're interested, there's a reference here which was recently published in IEEE Power and Energy magazine. So I said that this is maybe a little bit futuristic at the moment. So that's the evolution of DR management. So like not that long ago, we were simply treating distributed energy resources as troublemakers. But now we are moving towards a fully optimized future where we optimize those resources in a similar way I mentioned before, but we are not quite there yet. Actually, there was a plan to commercialize those network-aware coordination that we trialed on Bruni Island, but it turned out that the industry is not quite ready yet for that level of sophistication. So at the moment, we are here where we try to solve the same problem, but in a, let's say, heuristic way. And this is done using dynamic export limits. And this is what my talk is about. So what are those dynamic export limits, or operating envelopes, we also call them? So the baseline, you can consider the network company just imposes a blanket export limit on what customers can export, and that obviously doesn't take into account the operating condition. It's highly suboptimal. So the idea is to come up with a dynamic operating envelope that dynamically adjusts the amount of power customers can export into the grid to maximize basically hosting capacity while meeting network constraints in the network. Now, the challenge with the computation of operating envelopes is that requires full observability. So mathematically, I mean, you can formulate the problem in different ways, but essentially it's maximization of network hosting capacity, so you can maximize the minimum export limit across all customers, across all time slots. And that's done for, I don't know, for the next day, maybe for the next week. And this is subject to network and power balance constraints and DER operational constraints. And just to remind you, in the fully optimized approach I mentioned before, you get those operating envelopes implicitly, right? They are not explicit in the formulation. So here we are trying to solve this problem approximately. Now, this can be done day ahead using demand and PV generation forecasts. And again, the important motivation for this work is the fact that distribution service operator, or we call them distribution network service providers, they are not quite operators yet, don't have access to real-time smart meter data. They can buy that data for the previous day from the retailers who collect the data, but they don't necessarily have it. Unless in Victoria now, the coverage, smart meter coverage is 100%, so every customer has a smart meter, but that's not the case in other states. So which means that DSO need to compute those operating envelopes with only partial observability of both the networks and also what the customers are doing, and that's a challenge. So the contribution of this work is, so actually in our previous work presented at the PSCC, we proposed an optimization framework, stochastic optimization framework for the computation of operating envelopes. And in this paper, we focus on how to generate probabilistic forecasts of PV generation and load demand so that the DSO can compute those operating envelopes that are robust to uncertainty. And specifically, we use conditional generative adversarial networks, again, assuming that the DSO has access to historical smart meter data and PV generation data, and real-time data with one for the previous day, right? So it doesn't have this information in real time. So what we want to do, we want to generate a probabilistic forecast that the DSO then uses in the calculation of operating envelopes. So just quickly, we split the historical data into different sets. First, we generate point forecasts, then we generate residuals, then finally we generate probabilistic forecasts that then feed into this chance-constrained optimal power flow model that is used to compute operating envelopes under uncertainty. So you can think of that as a bi-level framework where the DSO computes those operating envelopes. As I said, we presented this work at the PSCC, and the focus of this paper is this bit here. they submit those operating envelopes or dynamic export limits to the customers, and they optimize against those limits using their home energy management system. So I'll just briefly go through that. I won't really dwell on that. So that's the home energy management problem of every prosumer. So we assume they have rooftop solar and a home battery. So this export limit is basically this bit here. And this is submitted day ahead by the DSO, and they optimize against that. So they minimize, essentially what they do, they minimize energy expenditure. So this here is the time of use tariff. That's the feed-in tariff. Basically, they get paid for the power they export to the grid. And there's this chance constraint AC OPF model that we presented at the PSCC. Is essentially same as before. So we maximize network hosting capacity. And this is subject to, again, network security constraints, maximum power export limits, DR operating constraints, which I mentioned before, and stochastic change constraints. So the network model is an SOC second-order cone branch flow model. And that's so the DR operating constraints I mentioned before, maximum export limits. So if you're interested in details, they are in the paper presented at the PSCC. So these are the chance constraints. So again, in the interest of time, I won't dwell on that. So I'll just briefly explain how this SIGEN structure works. So essentially, you have a generator that generates residuals. And then we compare that against the training data set. So we have this generator, we have the discriminator that essentially checks whether the residuals generated by the generator are realistic, right? If they are statistically representative. And we also use this condition. So the difference between GAN and SIGEN is that we use this condition C, which we add as an additional input to improve performance. So I'll skip through the math. So that's really, details are in the paper. So just focus on these conditional inputs. So to improve performance, we take historical data of the previous day, so 1, 2, 3, 5, 7, 14, and 3 weeks behind. And also we use the day type, weekend or weekday, and season. So skip to the results. So these are now the probabilistic forecasts. That's for the load. So we can see that we have this point forecast plus the variation or the residuals around that point forecast for load and for PV generation. And this information is fed into the chance constraint AC OPF model computed, so used to compute the operating envelope. So this is the probability distribution for the load forecast at different times of the day, and the same for solar generation. And finally, some results. So we use a fairly simplistic case study, 25 bus test systems. So each customer, again, was assumed to have a PV system and a battery system. And we, for the sake of simplicity, we assume a fully balanced operation, which allowed us to represent that as a single-phase equivalent. And these are some representative results. So as you can see, on days with high PV generation, the DSO has to reduce the export limit to prevent over voltages in the network. And this figure shows the power profiles for all 25 customers. So just some directions for future work. So one limitation of this work is that we assume that all the distributions are Gaussian, which obviously is not the case. So we are now working on replacing that with non-parametric distributions that can capture other kinds of more realistic distribution. And the challenge is how to include them into the optimization framework. That will also require quite a bit of work. So we're currently working on that. And another direction for future work is that we want to be able to generate forecasts that are closer to real time. So this is essentially to check this condition, check this condition, this assumption that the DSOs can only get smart meter data for the previous day with a 24-hour time lag. So if you move closer to real time, how does that improve the performance? And this would be like feeding into the discussion we are currently having at with the network companies on the regulatory level to change the regulatory practice to actually enable everyone to do this better. So.
All right, perfect timing. Thank you. So we are ready for questions. Any questions, please? I see one there, so that's, well, you are closer to the mic, or whoever is, I don't know. Yeah.
All right, thank you, Gregor. Hamid Zaripur, University of Calgary. So I have a question that is related to your work, but not directly on the technical side. So given that this growth of behind-the-meter kilowatt hours generated by people, so there is a loss of revenue for the utilities, and the utility death spiral is happening. So what are the utilities are doing to compensate the lost revenue? So what are the tricks in their bag?
Yeah. No, that's an excellent question, and there's actually a name for that. It's called a death spiral. So essentially what means that when people adopt rooftop solar, the utility has to charge more to recover the same revenue from the customers who are without solar. That's a well-known problem. So one solution is, first of all, reduce feed-in tariffs. So that's one solution. The second solution is that where network companies actually came up with an idea of charging customer for exporting power to the grid. So they still get a feed-in tariff from the retailer, but the network company will charge them to export power. So essentially what that means is that implicitly they create an incentive to increase PV self-consumption. But that doesn't quite answer your question. So this question, the revenue, so one solution, but this again, it's not optimal, is to increase capacity charge.
What they are doing?
That's yes. Well, to be perfectly honest, I don't know. I mean, that information is a bit opaque. If you are like, maybe this is a bit naive, but coming from an academic, I want to change this regulatory framework and the structure, which is currently very siloed, in a way that enables everyone to extract maximum value from the devices that sit behind the meter. How that's done, that's probably beyond my pay grade, but okay. It's an interesting challenge, very interesting challenge. Yeah.
Maybe electrification of the transportation. That's additional revenue. Thank you for that. Now we have one more quick one.
From University of West of Finland. One of the problems that generally we have for extracting data for the behind the meters in the smart homes and so on is electric vehicles that can make lots of problems for the forecasting of the even what is the behind the meters for getting from the renewables, because they are kind of uncertain and can make some kind of merge with the already stationary batteries that we have. Could you please add some comments that how can we fund that, how much of the power that we are going to forecast or use it for the OPF and so on can be from the solar generation, or some parts are from the just some parts of the stored energy in the battery of electric vehicles?
Okay, so here we focus just on the power exchange between the customer and the network. So we don't really care what happens behind that point of common coupling, right? So we don't explicitly model. There might be, this home energy management system might include other devices, flexible loads, electric car, but we only focus on the interface between the customer and the network. So we only care about the network exported. We are not explicitly interested in how the composition of the load and what other devices might exist behind the meter.
So for your forecast, it doesn't have any impact on the, for example, the
okay, I see what you mean, yeah. Well, there are two elements. So I guess your question is, how do we forecast the load given that the load...
Exactly.
So, okay. We don't explicitly consider that. We just have this smart meter data, which is the aggregate load for the previous day or whatever, and we just forecast that. If you can include, you can improve the forecast by including metadata. So if you assume in your forecast that you also know the composition of the load, and you, for example, you have like pool pumps, electric vehicles, HVAC systems, you can use other information, weather data, maybe usage patterns, to help you with the prediction, but we currently don't go into that level of detail.
Okay, very good. Thank you, Gregor. Coming to the last paper in our, not the least, of course, Mohammed Awadallah will be presenting. You there, Mohammed? Okay.
Hi, good morning. Thanks for the organizer. It's a pleasure to be here. And in today's session, this is me, Mohammed Awadallah, PhD student at McGill University. And this work is a joint work with, between me and my supervisor, Francois Bouffard. And today, I'm going to talk about the influence of stochastic dependence on network constraint for unit commitment problem. So in this work, we'll try to see the impact of the correlation in the data coming from the demand and the renewable resources, and how that's impact on the congestion on the transmission line for unit commitment problem. So I'll start with the outline of the presentation. At the beginning, I'll present the unit commitment problem, the background and the formulation. And then the second point, going to the network constraint screening, which is the main part of the work, the current existing approach, and our proposed methodology, which we call it umbrella constraint discovery, and then how we can, and then the uncertainty model that we use with the umbrella constraint discovery, then case study and conclusion. I'll start with the unit commitment problem. It's a fundamental optimization tool for power system operators. Here in North America, it's been used to clear the day-ahead electricity markets, and by optimizing the generator's output and the on and off status of the generator while satisfying engineering and system physical constraints. The challenge of the unit commitment, it's a large-scale mixed integer program, and it's an NP-hard problem. So this is the motivation of our work. There are to find a way to solve unit commitment to optimality in a computational efficient manner is a popular research topic. So the today focus will be how to, it's a step towards running the unit commitment to optimality in a computation efficient manner. So I'll present the unit commitment with a few assumptions without listing the generality of the problem. Would like to, oops. This is the objective function. It's a linear objective function trying to minimize the operation cost of the generators. It's wide system balance equations. Here the generator's boundaries. And here we have the line, the transmission constraints equation. And here we have the binary variables related to the generator. So the goal is, in this work, the goal is, in unit commitment problem, this constraint is the largest number of constraints you will see in the unit commitment problem. So can we do in a way that we're trying to eliminate these constraints that doesn't affect the problem solution, so we can run the unit commitment in a more efficient and more faster way. So the next part for the network constraint screening, there are a couple of work in literature We'll focus here on optimization-based method, which is basically it's a convex relaxation of the unit commitment problem. So as you can see in this graph shows it's in a 2D graph, and here we have 5 sets of constraints. So these sets of constraints, some of them are redundant, and if we can eliminate these redundant constraints without affecting the original problem. So that's our goal in this work. And you can see that it's the visible region can be described using only C4 and C5 and C2. And C3 and C1 are redundant constraints. This is in just 2D. In the larger networks, we'll have more redundant constraints, transmission constraints, so that's the goal. So I'll present the umbrella constraint discovery method. It was proposed by Amir and Francois Bouffard in a paper. You can find that in the paper, but it was proposed in a different context. I'll discuss this here briefly in the next slide in the context of unit commitment problem. So the umbrella constraint discovery, it's a mixed integer linear programming problem. We introduced a binary variable that can define the number of lines that can hit or surpass the power flow at specific lines. So if I want to go to explain this method, I can, the shortest way or by intuitive way to explain this method is as follows. We have these two, the equation 9 and 10, they couple or they pairs the original line transmission constraint with another equation, and we can see that to have a Qn, which is basically the generation minus demand, that to fulfill these two equations, ZL to have to be 0. In that sense, VL, which is the decision variable that we are using to pinpoint the umbrella constraints, it's going to be 0. Otherwise, ZL will be positive, and then VL will be 1. So in that manner, we're checking these two equations while we are relaxing the rest of the constraints. So we'll go with the generation and demands to the boundary, to the max, and then we'll see at which point, at what line constraint we can hit the boundaries of the transmission line. So this is an iterative method. It can find that by revealing the vertices of the relaxed version. So to explain that a little bit, the method can find the vertices, the whole vertices of the visible region, and then we'll say, okay, this is the constraint, and this is the constraint related to certain vertex, and the iterative method works as follows. It can pinpoint the first vertex with the most intersecting line constraints, and then goes to the second one with the fewer line constraints till there is no other constraint or transmission line that shape the visibility region. So, the basic, the contribution or the main contribution of this work, the modeling of the residual demand of this problem. So the conservative approach has been in literature to model the demand with the boundaries without considering the spatial correlation. And what we are proposing in this work, we propose to tighten this relaxation by capturing more accurately the net load correlation. Here, this is we propose the polyhedral uncertainty set, and the steps to construct the polyhedral uncertainty set as follow. We have the historical data, and then we'll compute the mean vector and the covariance matrix, then we'll obtain the principal component of that covariance matrix, then we'll reconstruct the original data based on the principal component and the eigenvalues of that data set, which we call it scenarios. Afterwards, we construct the convex hull using the constructed scenario from the previous step, and that can be formatted as follows. So the pictures can tell more than words. The blue dots are the original scenarios, and you can see that the original, the orange lines, these are the projection of the original data into the principal components. So then, when we project these data into the main principal components, then we compute the convex hull, and that's going to be the polyhedral uncertainty set that we are using to tighten the convex relaxation. This is the same methodology that I presented in the previous slide, but with adding now the polyhedral uncertainty set. Here we're going to go to the case study, to the comparison and performance evaluation. This is the benchmark that we've used from this paper. I think one of the authors was around here in the conference. Yes, yes. So the idea is similar. That the idea here in this convex relaxation tool, it's basically maximize and minimize the power flow on each line, and then see in both ways, minimization and maximization, while relaxing all the decision variables. In the next slide, I'm going to talk about the performance evaluation, the two performance evaluation that we have used in this paper, in this work, the percentage of the umbrella line constraints, the retained constraint, how much reduction we achieved from this methodology compared to the benchmark approach, where in the benchmark approach, I would say robust box shape of the uncertainties is modeled, and the second metric we've used is the computational time needed to screen out the redundant constraint. It's not the how much we achieved in terms of unit commitment, but it's on the methodology itself. So briefly here, the solution time for constraint screening approaches. We called our methodologies data-driven UCD, umbrella constraint discovery, and this is the benchmark. You can see that we achieved much savings in computation time, considering the IEEE RTS and the IEEE 57 buses, the 73 and 118. And the one point here, the benchmark approach, it solves the linear problems. So you can see that the computational time it's increasing in a linear manner, but here is not the case, because that depends on the number, that depends on the vertices and how much lines or umbrella lines we have. But the one takeaway from this, that whatever the system grows, the growth of the system, more buses will see less and less redundant transmission constraint. So that means in terms of scalability, the method will perform well. That's what we're doing now on a practical large, big system. 2 minutes, yeah. I'm closing now, thanks. Here, we'll show the percentage of the umbrella constraints or retained constraints while we're considering different uncertainty levels. And we can see that when the uncertainty grows, our methodology, it's more conservative, so we'll achieve less number of retained constraints compared to the original, to the benchmark approach, where the the uncertainty has been modeled in a less conservative way. To conclude that, we managed to screen out the constraints that are not affecting the visibility region, and the current direction is in our work is to find the trade-off between tractability and robustness using the polyhedral uncertainty set compared to the convex set, and how we can utilize the principal component, how many principal components we can use to achieve the goal without considering the whole without considering all the principal component. And lastly, would like to draw lower bound theoretical boundary and robust and probabilistic guarantees for the proposed polyhedral uncertainty set in a general robust optimization framework. That's it for today. Thank you.
Thank you very much. Okay, folks, we have a perfect timing. We have 20 minutes left. We started 10 minutes late. Combined, we have half an hour. We're going to stay 10 minutes into the break. And Mohammed, what we're going to do is ask you to sit at the panel together with other panelists. Please come. And then we will let Mohammed answer the first questions. Okay? And then we continue with the panel. So that's how we're going to do it. So panelists, please come in. The ones that have questions for Mohammed, please raise your hand or line up. Anybody has a question for Mohammed while we are all settling here? No? Okay, then we will just, oh yeah, there's a question up there. And so I will just handle this one question and turn over to Robert for the panel moderation. So is that okay then, Robert? All right. Go ahead. So this is aimed at you.
Yeah, the Shafiq University of Oslo. Thank you for your presentation. Very nice method. I have one question. I'm not sure that is your model can increase the non-convexity of the problem, because one of the problems that we have for unit commitment or other methods for example, when we want to use it for the clearing the market and so on, is the non-convexity of the problem. And you already added the VL, which is the binary variables, and it may increase the non-convexity or not.
Your question about if the unit community itself, it wasn't...
Yeah, because one of the problems that we like to have a totally linear problem,
yes,
but correct. When we have some binary variables, it may problems for getting the global optimum for sure. But you added some new binary variable, I guess, and my concern is just increasing this non-convexity and finding the nearly global optimum for the system.
Yeah, so that's a good question. This method we're using, it's a kind of pre-processing, can be done offline to eliminate this. We don't have in offline in advance. If you have your forecast, if you have your historical data that you can use, whatever for how long you want, then you can run the mixed integer linear program in advance, in offline manner, so you can save all this time, like all these binary things in the unit commitment in the real time. So it's going to be run much faster. That's the goal. But what I'm trying to present here or highlight that the method can even shrink the uncertainty set more than the conventional modeling for the residual demands. But is that clear now?
I don't ask actually about the problem is time consuming or not. I'm talking about the error of the final solution that you reach, and is error might be a bit higher than the normal ways if you added some new binary variables. In general, it depends on the way of your decomposition and so on.
Could you repeat the question again? I didn't get it, sorry.
Okay. I'm talking about the final error of your system, of your model the system. Yeah, the gap of the
optimality gap.
Yeah, the optimality gap of the system.
Okay.
And could you please explain a little more that if this gap is will be higher or lower?
So for the level that I'm using the smallest range of the uncertainty, like 10%, the optimality gap was 0, and that's what I'm doing now to not to show the optimality gap in terms of empirical way from the methodology, but to derive a theoretical bound, lower bound for the optimality gap compared to the considering the whole thing.
Thank you.
Thanks.
Patrick? Yes. Patrick Passetti from RT France, so perhaps I can have a different question, but I can continue with you. But so I don't understand why, or you don't try to just to write down the full problem and go to a mixed integer linear programming problem that is doing crazy stuff for pre-solving. So did you try to formulate a big problem and go to Groby or Cplex and to solve that? Why it's not possible? So it's not very clear for me. And yes, and second question, more on a uncertainty set. So what the big problem we have is that we have this multimodal distribution. Yes, so then it's very difficult to do that that kind of PCA on that. We don't understand what we are doing. So a multimodal distribution. Could you comment on that? So 2 points. Why we are not going to classical mixed linear programming and let the pre-solving doing the job, and the other one, the modeling of uncertainty, where you have this multimodal distribution.
Yeah. Thanks for your question. For the first part, we can solve the mixed integer linear programming for unit commitment, considering the usual way with the whole set of constraints. We can achieve that, but with this methodology, if we can run it in advance, we can achieve very computational savings. If we can solve the unit commitment in 15 minutes, 10 minutes, whatever, we can solve the problem in 2 minutes or 3 minutes. That's in a way, but I think
you know what happened in the pre-solving of this mixed integer linear programming? There is this first pre-processing that tried to get rid of all the constraints, and I have some examples. They go to 1 million to 5. Yes, you know, in this pre-solving, and then internally they just solve with these 5 constraints, and there are a lot of very nice engines that are doing that. It's a bit of black box, but but you know, it's impossible to compete against them. We try many times to do what you are doing, and we never be able to do more than what they are doing inside this mixed integer linear programming problem.
Okay.
Did you try really to formulate the problem and to go to the very best implementation? Of course, if you implement yourself something in a very naive way, of course it's
yeah, I mean, so the first idea about the work, what I fit it here in the unit commitment, the idea is this methodology can be like I agree, the big impact can be in a problem where you have these kind of bi-level problems, but at the end of the day, this methodology, this convex relaxation can work either in unit commitment, or if unit commitment is combined with another problem and an inner problem. So when you have binary variables, and binary variables it's going to take a lot of time. So if we can save some time on this, why not?
Okay. I think we need to move on to the discussion. So who wants to start? Please.
I have a question for Amina. You presented solar curtailment as a bad thing. Could you think of potentially solar curtailment being a resource? So you reduce load, you reduce solar curtailment for short periods of time. And my question is then, what is the relationship between kilowatts curtailed versus kilowatt hours lost? So the benefit of kilowatts is significant. How many kilowatt hours are you really curtailing over a longer duration?
Does it work? Yeah. Okay. Actually, we think about curtailment in a bad way because in Belgium you have to compensate if it happens too often. So that is a cost. So it depends if in the end the cost is bigger or not than regular production. So that was your question, right? The difference between what we produce normally and the one that we produce with PVs? Or
I guess indirectly. So there have been reports coming out of Germany that show that, what is it, a few % of annual kilowatt hours curtailed can lead to 200% increase in hosting capacity, for example.
oh yeah, no, we.
So the kilowatts versus kilowatt hours seem to have very, very beneficial sensitivities.
Yeah, actually, that's the thing. In Belgium, you have to compensate if you curtail too often. So you have the hour in that, not the voltage the power you curtail. Sorry.
Okay.
So yeah, it has a time in it and the frequency you have that it happens to. So I guess yes, I did use that. So when you check the entire problem in the maximization, we take the entire month. So we guess that at some point you will be able to produce more. So it's okay if you have to curtail, if at some point you compensate. So I do agree with you, and it does have an impact on the time and how many you're able to produce. If you have to curtail like 1 hour, but you have a bigger capacity at another time, it's still better, and you have to curtail. And in that time, yeah, it's not bad, but
it's beneficial.
It's beneficial, yes. So I agree with you. You maximize your hosting capacity doing that. But it was like, it felt it was taken into account in the optimization problem. Right?
That makes sense. And if I wanted to throw in, this is a bike question. If I wanted to throw in load, like electric vehicle charging, they have a very similar nature as your PVs. Can you combine load and PV into your formulation?
We actually thought about that. We did separate them, so I did run this tool with EVs, but we didn't combine them because it takes a lot of time to run. The genetic algorithm is not fast, to be honest, and the more you add things in it, the more possibilities you have. So it is not time feasible as uncertainty. So it will be interesting, and this should be the next step, to be honest, because in the network you have now, you would have both.
Yeah.
And I think they would compensate at some point. So if we have a smart way to put them together, it would be amazing. It would be like the best idea, I guess.
I agree.
So yeah, I think it would be a next step. The step before, we computed the hosting capacity, and we did it also separately because it is hard and not feasible computationally for the moment to do both at the same time with this tool.
Okay. Thank you.
You're welcome.
So we'll move on to the next question.
Misha Chertkov, University of Arizona. It's probably to Gregor, but maybe actually extending on distributed energy resources and the point which you made, which is of course, applies to Australia, also applies to, well, to Arizona where I live. A lot of sun and solar production will grow, and you suggest to turn it from a problem, right? Problem because too much of it, into a solution. So I wonder if there are new innovative suggestions or stories coming from demand response side, and specifically we now hear a lot about computer farms. Those are of course big, and they are not under meter, right? So however, we also hear a lot about distributed computing and edge computing. So basically, which possibly can be behind the meter and possibly in all of our houses. So I wonder if this is in considerations, and it can be kind of paired with solar, right? So all of us have computers, and we can crowdsource it for whatever tasks. If you thought about that, if it is under discussion, so what is the situation?
Thank you. So we haven't really thought about distributed computing. I guess the bottom line is you try to consume as much as possible what is generated. So I guess that's the solution. So electric vehicle charging behind the meter, it's one way. Currently in Australia, unfortunately, it's not, there's no push from the government, no incentive for the government to incentivize the uptake of electric vehicles. That would be one solution. In the context of data centers and large computing facilities, there are now, I've seen proposals to locate them where there's a lot of solar resource because it's so much cheaper to generate power. But I haven't seen any discussions on distributed computing. I guess, again, the bottom line is try to create as much load as possible close to the source, because the bottleneck is the low voltage secondary distribution.
Yeah, next question, and then Claudio.
So just to connect the dots, we use the term hosting capacity very loosely now. If you think about what Kostas is talking about, you have adaptive voltage adjustments to change the regions to make sure that things are stable, in particular with inverters. We saw, I think, Gregor, it was in your colleague's presentation, you put these inverters on and you have all sorts of harmonics and bad quality of service and everything. So I haven't seen one single paper which defines hosting capacity very carefully, that takes into consideration all of that. So we do the optimization, all the formulations optimization. Is there any concern on the utility side when you talk to them, beyond just staying within steady state limits? Or how do you roll in the quality of service and dynamics and give incentive, for example, what Costa is saying? It's a great idea, but it doesn't enter your optimization and sort of standard definition of hosting capacity. In New England, when they do hosting capacity, they do sort of worst case. What is the first stability limit? What is the first voltage limits? And what is at the end, the steady state feasibility? But it's not very systematic. I think we need to, as a community, to sort of sharpen the definition a little bit.
Yeah, thank you. So my take on that is, if I put myself into the utility shoes, they solve problems as they come. So the immediate problem was to deal with what happens when you have simply too much solar. I haven't seen any discussion. I mean, this pops up occasionally, power quality, harmonics, all of that. But my understanding is that it currently doesn't cause problems to the extent that they would need to actively do something about it. And also, utilities are not in the business of coming out with comprehensive...
Voltage is very critical. Voltage is really critical.
I think you have to use the microphone.
Oh, yeah, over voltage, but not voltage quality. So the shape of the voltage waveform, which is supposed to be sinusoidal...
No, that is... Yeah, but voltage, still don't see good incentives. I spent 15 years with my startup explaining to utilities that voltage matters. And it actually, even steady state adaptation that Kostas is talking about, it's really not incentivized to do.
I agree with you, yes. And again, my understanding is that those problems currently are not so big that utilities would actually do something about it, but yeah, I leave it at that. I don't know.
Yeah. Claudio Canizares, University of Waterloo. My common question is for Kostas. I found it very interesting that you develop a technique to basically send these orders to P&Q to the ADN, to the distribution system. We work on the other side, developing a mechanism to, once you have a PQ, to try to coordinate all these resources now in a distributed way. Now, the problem I found with that is that, well, we had to develop a centralized mechanism, which assumed that I had to somewhat motivate these resources to participate, to do this, provide this type of service. You show the value of that service. So I think there's got to be it is more of a conceptual problem, I guess somewhat related to what Maria was saying, which is, how do you motivate these, how do you make this happen? Because they are interested in their own things, and they are doing their own things, and then they get this order, which is useful for the transmission system. Can you elaborate a little bit on that, comment a little bit on your vision on how you see this? I'm not clear myself, so.
Thanks, Claudio. Yes, I believe there is a big gap between where we are now and where I I am aiming at. So the idea is that in my approach, I consider that there is a local controller at each MV feeder or substation and has full knowledge of the network, which can be done with state estimation, and can send signals to certain controllers, some of which are like could be switch capacitors, as Patrick said, but also could be converters that accept to be controlled by this central controller. So this is the concept. I think in the future, having less and less capacity from central generating stations to do the system control, we will have to go to this level of distributed control of the transmission network through the distribution. And I think this is the paradigm for the future. But we are not there yet, this I accept. Now, concerning the technique, we are using the OPF, who will give the all the voltages. So you have the voltages, voltage set points of each voltage controlling device. So this is doable. I mean, this solution of the third optimization problem, which is I take the set point of the consumption and I try to adapt to it as close as possible, will give you set points, and then your devices will follow the set points.
Sure, yeah, I can see that, and the way we saw this problem was similar like that. Somebody gives me the orders, and then I follow it distributed. Thank you. I had a question for Gregor, which is this issue that you show, this significant participation of solar at the low voltage level, at the residential level, creates a lot of these issues of the dark curve, right? California is dealing with that. And I wonder, how is the Australian operator dealing with these issues? How are they managing this problem?
Thank you. In the figure I showed, not sure if you noticed, there's no coal generation left. So it's only wind, solar, and there are actually a couple of gas turbines that need to run to provide inertia. And the connection to Victoria, it's quite weak. So in South Australia, that's not too big of an issue. NAM-wide, it is. And it's, especially in Queensland, it happens quite often, even now when the prices in the morning or during the night can go over, I don't know, even a few $1,000s per megawatt hour. During the day, prices can be negative, and because there's so much solar. So to answer your question, I haven't seen any discussion about what to do about that curve. What I do notice is that coal-fired generation retires way sooner than everybody planned they would. So that they are just exiting way sooner than, because they're simply getting out of business. They cannot make enough money. Dealing with so as I said, I haven't seen any discussions to discuss this duck curve explicitly, but we expect that in 10, 15 years' time, there won't be any coal generation left, so which means then this duck curve won't be an issue anymore. Yeah. We don't have nuclear. Actually, it's in our constitution that prevents us from building nuclear.
I think we have to move on. We have two long lines here. So maybe start over there.
Okay, thank you.
Your name as well.
Hamid Zarepur, University of Calgary. So probably this connects the work by Amina, Stephen, Gregor, and Kostas, and maybe Abadullah. So we treat transmission level studies and analysis always as balanced. And now we have behind the meter injecting a lot of things on different phases probably, and it's becoming significant. And Stephen is presenting a model. How can you, write equations for, three-phase power flow and stuff. So do you see a need for that? Are we going towards a world that we can no longer safely assume that the transmission system is balanced and we can treat it in a single line type of analysis. Is that drives your work, Stephen? Or do you see evidence, Gregor? Thank you.
My answer is very simple. I think that the rest should answer most of the question. So I'm more motivated for distribution system analysis. Yeah. So whether there's enough unbalanced in transmission system, maybe others can comment on.
Yeah, my comment would be, if you look at the canonical optimization problem that I showed in my slides, you can consider that the gold standard, right? And you try to come as close to that as possible. And if you don't have a detailed model of your low voltage network to be able to compute operating envelopes, then you cannot really reach that optimal. So that would be, implicit answer to your question. That would be the reason why network companies should put effort into developing models of their low voltage networks. Otherwise, if you don't have an observability of even like detailed models, then you cannot really manage like this massive number of resources.
Yeah.
So, John Simpson, University of Toronto. My question is inspired by Stephen's talk, but is to all the panelists. So, when we think about the representation of power flow equations, we have several different coordinate systems that are sort of used, depending on personal preferences and possibly distribution versus transmission. So you can do polar coordinates with bus injection, rectangular coordinates. You can do branch flow model. And it seems to me that we have no reason to expect that all of these models should numerically behave the same way when you start interfacing them with interior point solvers and Newton-Raphson. So I guess I'm wondering if we have any path to systematize our knowledge about the different power flow representations and how they behave numerically.
I can only answer from our case. We use the Cartesian coordinates so that the problem is quadratic. And we try to keep it this way to not only for the solution, but also to try to get some analytical results on the solvability and the convexity of the problem.
A good question, but I don't really have an answer. I just want to clarify. The device models that I talked about, they are very simple. Everything's linear. There's a bit of a complication that Maria mentioned, that if you have the delta, then there's this arbitrary constant you have to be careful about, right? Again, probably for your problem, you have enough information to determine that. Otherwise, maybe you can approximate that. If you approximate the arbitrary constant is 0, it may or may not be accurate. Again, depends on that. Depends on your problem. And therefore, the device model, which I think really is the key difference between three-phase versus single-phase, they are very simple. I'm not sure they will add a lot, change much on the numerical issues. I think the numerical issues will exist, will remain, and that comes really from the power flow equations. Okay, but I should clarify. On the network equations, you could just use IV. Everything's linear, but that relates only the terminal variables of all those different devices, including transformers and so on. Now, if you have constant power device, or the power is the variable that you control rather than the voltage current, then inevitably you will have nonlinearity in your overall model. And then the numerical issues may rise there. But I think the network equations themselves, you could have somewhat orthogonal way to deal with that, separate from the complications that arises from the nonlinearity in the devices.
So we only have 2 more minutes, so maybe only one last question. I don't know who was first, maybe
okay,
you.
Yeah. Okay, I'm Antonio Simões Costa, Federal University of Santa Catarina, Brazil. My question goes to Stephen. Your mathematical approach for three-phase power flow seems to be very interesting, although I haven't read your paper yet. But I was just wondering how your method compares with other approaches, such as the quadrupole approach from the Kirsten book, that seems to have the same inspiration, that converting internal variables to external variables, but then using inspired in circuit theory principles rather than mathematical tools.
Yeah, that's right. I think that there's nothing new in my paper. So I think that the new thing is perhaps it is a unified approach to explicitly think about three-phase devices, and they have this separation of internal and external model. I mean, this idea is spread around different papers. But I think if we don't explicitly do that, we often make assumptions. For example, neutrals are grounded. They may be grounded with zero grounding impedance, so on, which sometimes we're actually not aware of. And therefore, we will get the equations that are simplified, but may or may not be accurate enough for your problem. So the sort of the way I think about that is that if you develop this method, which is, by the way, it's a very simple method, everything is linear, right? If you develop the method for the most general case, things actually simplifies. Actually, conceptually, everything is very simple. You don't have to worry about 20 different cases. Oh, this device is grounded, that device is neutral or not, and so on. Yeah, so I think that's really more of sort of the clarity that results from thinking about the problem more generally.
Okay, thank you.
I'm not sure I answered your question. But.
Okay, we have to close the session, so I would like to thank the speakers. Okay.